In 1905, Albert Einstein published 4 papers while working in a Swiss patent office. He was only 26 years old. On the electrodynamics of moving bodies was the name of his paper on special relativity. Electrodynamics refers to electromagnetism we discussed in the last lesson. Einstein asked, in what frame of reference is electromagnetism valid? We learned in Lesson 7 that motion is valid in any frame of reference, but what about electromagnetism? Are the electromagnetic waves the same no matter where you are? The answer is yes, and that is special relativity. Relativity says all laws of physics are the same for all observers in uniform motion. As we discussed in Lesson 7, uniform motion is moving in one direction at a constant speed. You can do physics anywhere you want and get the same results, including electrodynamics. This led to some very strange consequences, especially for space and time. Knowing that electromagnetism was valid for any observer moving in a uniform frame of reference, and that the speed of light was 670,616,529 miles per hour, Einstein forever changed our concept of space and time. For future reference, the speed of light is also known as c. Therefore, if electromagnetism is valid for any uniformly moving frame of reference, then c must be measured at 670,616,529 miles per hour by everyone. Can you see where this is going? Well, you will. The speed of light is measured the same for everyone, even if they're moving relative to each other. What does it mean to be moving relative to one another? If I'm driving my car and I pass you standing on the road, we are moving relative to each other. Remember, driving in my car, I can just as easily say you are moving relative to me as I am moving relative to you. If I drive by you at 60 miles per hour, it is just as correct for me to say I saw you moving at 60 miles per hour as it is for you to say you saw me moving at 60 miles per hour. Let's say after driving past you, I continue in my car heading north at 60 miles per hour, and another car driving south passes me, also driving 60 miles per hour. I will see that car moving at 120 miles per hour, the 60 plus 60 miles per hour. We add our speeds together. When the other car passes you, since you are standing on the road, not moving at 0 miles per hour, you will see it pass at 60 miles per hour, 60 plus 0. Now here is where it gets strange. If instead of a car, I pass a beam of light coming towards me and measure the light, I will measure the light moving at that 670 million plus miles per hour. Unlike when a car comes towards me, I don't get a measurement of our speeds added together, the 670 million plus miles per hour plus 60 miles per hour. Then when the speed of light passes you, you also measure that speed of light. What? Well, it doesn't matter your speed. You will always measure the speed of light moving at 670,616,529 miles per hour. Always. Let's make it even more dramatic. If you are standing on the road and measure a beam of light coming towards you, the light will be coming to you at that 670 million plus miles per hour. If I'm in a spaceship zooming away at half the speed of light, it is still coming at me at the same speed. The light is catching up with me, zooming away from it in the spaceship just as fast as it is catching up with you standing still. Think about how crazy that is. Here's another example. If you're playing tag, you will obviously catch someone standing still before you catch someone running. But light doesn't work that way. Light will catch them both equally. Whoa! No matter what we are doing, we all get the same value for the speed of light. Now let's see what all this crazy light stuff means for space and time.